Here we have a model of a bipolar junction transistor operating in active mode. A transistor consists of three terminals. One terminal is called the base, the other the emitter, and the last one is called the collector. We're asked to find the base current IB. We're going to do it using mesh analysis since we're modeling this transistor as a dependent source. So here we have a current-controlled current source at the collector terminal. So we'll form two mesh currents labeled here as I1 and I2. Here we're going to require a super mesh since the dependent source is included in both meshes. So in the diagram here, just redrawn on the right, and we have a super mesh as indicated by this drawing. Now we form at the bottom our KVL mesh equation. So starting at the bottom, we have I2 RE minus V gamma plus we have I1 going through RB plus VCC, and this expression is equal to 0. So what we did is just a KVL starting at the bottom right here and working our way around as shown. Now we have an equation that has two unknown mesh currents, I1 and I2. Since the two mesh currents have opposite directions through the dependent source IB, the currents I1, I2, and IB multiplied by beta are related by KCL as follows, where we have I1 minus I2 is equal to beta IB. Now this constraint supplies the additional relationship needed to obtain two equations for the two unknown mesh current variables I1 and I2. We also note, looking at this diagram here, that IB is equal to minus I1. Hence, we have from these two relationships, substituting I1 in here, we have I1 minus I2 is equal to negative beta I1. Solving for I2 yields beta plus 1 times I1. Now we substitute I2 in the super mesh KVL equation that we just did, and what we have is beta plus 1 I1, again this is from the KVL, minus V gamma plus I1 RB plus VCC is equal to 0. We note that IB, as we said here, is equal to negative I1, and when we solve for I1 here, this implies that IB is equal to negative I1, which is just VCC minus V gamma, and we know I1 appears here, so that's why we're solving for negative I1. That leaves RB plus beta plus 1 RE. So we solve for beta, and this is our final result for IB for this bipolar junction transistor operating in active mode. Again, this is just a model for a bipolar junction transistor, and we'll discuss this in later videos about bipolar junction transistors.